Welcome to day 18. We're going to start talking about verifying trigonometric identities today. We've talked about a lot of identities. We had the basic identities, where we had the reciprocal identities, where the cosecant theta was equal to 1 over sine theta. That was a definition. The secant of theta was equal to 1 over cosine theta. The cotangent of theta was equal to 1 over tangent theta, and because tangent theta is equal to sine over cosine theta, that means that this is a reciprocal, or cosine theta over sine theta. And of course we define a tangent theta as sine theta over cosine theta. We had the Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. 1 plus tangent squared theta equals secant squared theta. And 1 plus cotangent squared theta equal cosecant squared theta. One thing you can notice here is if you subtract cosine squared theta from both sides, you can also come up with a version of this that we may use a lot when we're doing these verifying trig identities. You get sine squared theta equals 1 minus cosine squared theta. Or if you subtracted both sides, or sine squared theta from both sides up here, you would have gotten cosine squared theta equals 1 minus sine squared theta. Those are things we'll learn to look for later. Here, 1 is equal to secant squared theta plus tangent theta, minus tangent squared theta. And here, 1 is equal to cosecant squared theta minus cotangent squared theta. So we've done a lot of identities already. Today we're going to verify. There's an infinite number of these identities that you can come up with, and today we're going to verify quite a few of them. Here's a real simple one. If we had tangent theta times cosine theta equals sine theta. Now, that may not be something we've already recognized, but when we ask you to verify this, I give you a statement, an equation, and tell you that it's true and ask you to verify. You work on one side of the equation, and try to use substitution. Substitute things that are equal. To make it equal the other side. I usually try to start with, typically, now there's some exceptions to this, but start with the most complicated side. Here, the most complicated side is tangent theta times cosine theta. If we can make that equal by canceling things and substituting things that are equal sine theta, we will have verified this identity. This is really an easy one, and one of the strategies that we'll employ sometimes is to change everything in terms of sine and cosine. Using those reciprocal identities and the identities we talked about up here. We can rewrite tangent theta as sine theta over cosine theta. That's a substitution we can make because those two things are always equal. So now we have sine theta times cosine theta, but sine theta times cosine theta, sine theta over cosine theta times cosine theta is the same as sine theta over cosine theta times cosine theta over 1, which makes this sine theta cosine theta over cosine theta, and the cosine thetas cancel each other and make just sine theta. And so what we have done by reducing this side, just using mathematical operations and legal substitutions, we have showed that this original side is actually equal to the right side. Let's look at another one. Tangent theta times cosecant theta times cosine theta. equals 1. When I see one with just a bunch of trig ratios multiplied together, this changing things into sines and cosines a lot of times is going to help you out because fractions are going to cancel things. So tangent is sine theta over cosine theta. Cosecant theta is 1 over sine theta. And cosine theta is just cosine theta over 1. Again, I started on the most complicated side. If we multiply those together, we multiply numerators, multiply denominators, we get sine theta times 1 times cosine theta. And on the denominator, we get cosine theta times sine theta times 1. But sine theta times cosine theta and cosine theta times sine theta are both equal. All those cancel and leave me with just 1 equals 1. We have verified that trig identity. Another strategy we'll sometimes use is to look for opportunities to use the Pythagorean identities. Sometimes this won't be obvious, but when I see an expression like 1 minus cosine theta over, say, sine theta, that doesn't look like something I can use the Pythagorean identities because I don't have any squares. But if I multiply top and bottom by 1 plus cosine theta, I'm really multiplying by 1, and when I distribute this, I get 1 times cosine, plus 1 times cosine theta, minus 1 times cosine theta. Those middle terms cancel out, and then negative times positive is negative, and cosine theta times cosine theta is cosine squared theta. And on the bottom, I get sine theta times 1 plus cosine theta. But 1 minus cosine squared theta, if we recall what we found up here, is equal to sine squared theta. So this becomes sine squared theta over sine theta times 1 plus cosine theta. Sine squared theta is just sine theta times sine theta. And so one of those signs would cancel out. But anyway, when you solve this 1 minus cosine theta, what I started thinking immediately was an opportunity to use the Pythagorean identities. If it had been 1 minus sine theta, I would have multiplied by 1 plus sine theta over 1 plus sine theta, and ended up with 1 minus sine squared theta, and possibly been able to use that cosine squared to change some things. Let's look at another example. Here's one. I'm getting these off the worksheet and I haven't verified them, so if we find one that's wrong, we won't be surprised. Hey, let's look at this. Which one's more complicated? I'm thinking this side is. So I'm going to work on the left side first, and I'm going to try to distribute and see. When I do sine times sine theta, I get sine squared theta. Sine theta times cosine theta makes plus sine theta cosine theta. And negative cosine theta sine theta makes negative sine theta cosine theta. Those are going to cancel out. That's nice. And then minus cosine squared theta. Middle terms cancel out, leaving with sine squared theta minus cosine squared theta. That's not something I can use the Pythagorean identity on, at least not in its current form. But what if I add cosine squared theta and subtract cosine squared theta? You see, I had sine squared theta minus cosine squared theta, and there that is. When I added cosine squared theta and subtracted cosine squared theta, I effectively added 0. That doesn't change the value of anything. But we know from the Pythagorean identities that sine squared theta plus cosine squared theta equals 1, and minus cosine squared theta minus cosine squared theta is minus 2 cosine squared theta. And that's what we wanted that to equal. So again, I had a sine squared theta and a cosine squared theta that looked like something I could use the Pythagorean identities on. So I decided to give it a shot and see if I could make that happen. I needed a sine squared theta plus cosine squared theta, but I couldn't do that without subtracting the cosine squared theta to add 0. But we got where we were going. Let's look at a few more examples. Sine theta times cotangent theta times secant theta equals 1. This one, I don't see any reason, no addition, subtraction. I don't see any reason to try to use the Pythagorean identities. So instead, I'm going to convert everything sines and cosines. Sine theta is sine theta over 1. Cotangent theta is cosine theta over sine theta. And secant theta is 1 over cosine theta. Well, when I multiply that together, I get sine theta cosine theta over sine theta cosine theta. And of course, that's just equal to 1. Here, let's see, 1 minus 2 sine squared theta. Now, both of these, either one of them, you can use whichever one you want. Both look the same to me as far as complicated. Let's start on the right side here and see if we can make it look like the left side, just because they're both just as complicated as the other. I told you, I'm looking for ways to see if I can use the Pythagorean identities. When I see cosine squared theta, I'm thinking that cosine squared theta we showed earlier is equal to 1 minus sine squared theta. So I'm going to replace cosine squared theta with 1 minus sine squared theta in this problem. So I get 2 times 1 minus sine squared theta minus 1. I just replaced cosine squared theta with something that was equal to. I'm going to distribute that 2. 2 minus 1 is 1. And that's exactly what I wanted that to say. So I've verified that identity. Here we are again. Now recall, we got several of the Pythagorean identities. I'm seeing a cosecant squared and I'm seeing a cosine squared. I'm going to see what we can do here and see. This is saying this should equal 1. That's pretty interesting. So let's take a look. What I see is a common factor of cosecant squared theta. So I'm going to factor that out first. Cosecant squared theta times 1 makes cosecant squared theta, and cosecant squared theta times negative cosine squared theta makes negative cosine squared theta cosecant squared theta. One minus cosine squared theta, what we showed a little while ago, is the same as sine squared theta. So I'm going to replace that. But cosecant squared theta is 1 over sine squared theta. Sine squared theta is sine squared theta over 1. This is sine squared theta over sine squared theta. That's just 1, and that equals 1. We verified the identity. Here's another one. We actually almost did this one just a few minutes ago. Look at this one. We could start either way with either side. I'm going to start on the right side again just because we just did this a few minutes ago in an example. But what I see here, because I've got things tied together with addition and subtraction, the changing things to sine and cosine, well, it's already in terms of sine and cosine, so that's not really going to help us. So I'm going to look for ways to use the Pythagorean identities. 1 minus cosine theta, I know if I multiply that times 1 plus cosine theta, I can come up with something to use the Pythagorean identity, but I can't multiply the numerator by 1 plus cosine theta unless I also multiply the denominator by 1 plus cosine theta. So this is going to give me 1 plus cosine theta minus cosine theta, those cancel, and going to be minus cosine squared theta over sine theta times 1 plus cosine theta. Well, 1 minus cosine squared theta, again, we saw that's equal to sine squared theta. Sine squared theta is just sine theta times sine theta, so one of those is going to cancel with this one. That's going to leave me with sine theta over 1 plus cosine theta, and that's what I was looking to get. So that's how we're going to do these Pythagorean identities.